2 examples of 4.7 focusing. With one specialised load balancer coming after the other, we got the ALB in 2016, the NLB in 2017, this is clearly a re-envisioning of load balancing that had been carefully planned. We see a somewhat similar pattern with firewalls on AWS, and they're also sets of rules and they mediate traffic. We had the security group and the NACL for a long time. Security groups were surely introduced when EC2 instances were in 2006, but the VPC service was only announced in 2009, 3 years later. Jeff Barr wrote about security groups in a 2010 post. I cannot say. Anyhow, these well-established firewalls are similar to elastic load balancing. In 2015, the Web Application Firewall was announced. This firewall deals with HTTP and HTTPS requests. Then, a revamp was planned. On the eve of the COVID pandemic, November of 2019, WAF is relaunched. The next year, in 2020, the Network Firewall is launched, a new product. So again, we have the set of rules that's specialised for web, layer 7, the application layer of the OSI stack, then for the network, and they're coming a year apart. The Web Application Firewall. In 2015, AWS Web Application Firewall was announced. As the name suggests, this is a firewall. This product bundles a number of features into one package. All these features hinge on the fact that, at root, this is a firewall consisting of a set of rules. Here's a screenshot from a 2015 webinar by Nate Dye. If a request matches all of the conditions in a rule, take the corresponding action. We've got some columns: order, rule, and action. I will refer to the firewall within AWS WAF as the WACL, Web ACL. We can note a few things immediately. 1. The WACL does not possess allow exclusivity. You can choose deny rules. It's thus unlike SGs. 2. You can choose from allow, block, and count. What on earth is count? Count must mean allow the traffic and count. We'll return to this issue. Notice how at the bottom of the image we can set a default action. This default action will be carried out in situations in which the traffic does not match any of the rules. This is similar to the default deny, an indestructible rule marked with an asterisk which lurks at the bottom of NACL rule sets. However, as you can see, this WACL allows you to allow requests that don't match any rules, and that's that default action. Should we say that ERC holds with WACLs? That's ERC, Exhaustive Rule Coverage, ERC. You could argue that it does, if you consider the default action to be a rule, on a par with the default deny at the bottom of the NACL rule set. So all entities are covered by some rule. The rules are therefore exhaustive. However, I prefer to argue that WACLs actually lack ERC, just like security groups. One reason is that the default action is not a rule. I think that WACLs are more similar to security groups, which display this behaviour of being a denial in themselves. The firewall is the deny. Recall that SGs deny everything until you install allow rules, as if punching holes in a protective plastic sheet. This deny behaviour is not attributable to any rule. I like to think that WACLs share this property of inherent permissibility, meaning inherent permission. I don't mean inherent allow. The only difference is that it's configurable. You can switch between the firewall being the deny, like with an SG, or being the allow. So you can configure the inherent permissibility. This is a screenshot of the console in 2015, the year that the AWS WAF was released, and we've got 4 steps. Step 1, name the web ACL, the WACL. 2, create the conditions. 3, create rules. And 4, review and create. The console states conditions specify the filters that you want to use to allow or block requests that are forwarded to AWS resources such as CloudFront distributions. There were free conditions at the time. Because the request had to have some element in common with the rule, they were called match conditions. There were IP match conditions, string match conditions, SQL injection match conditions. To be clear, conditions are distinct from rules. This is within AWS WAF. And, of course, they are distinct concepts generally. The relation between conditions and rules can be expressed thus. This is Jeff Barr. Rules reference one or more conditions, all of which must be satisfied in order to make that rule active. For example, one rule could reference an IP-based condition and a request-based condition in order to block access to certain content. Here's a quick timeline of some of the features with AWS WAF. So it came out in 2015. Then in 2017, we got these rate-based rules, a special type of rule. And then in 2019, they said, okay, let's revamp it. And we got version 2. Previous version was now called AWS WAF Classic. And we got managed rules announced in that year. So managed rules come in the year that Amazon Detective and Amazon Kendra are announced. This is the console in 2020. Set rule priority, it says. And we've got a name column, a capacity column, and an action column. The action is count, the capacity is 1, and the name is NAM IP set rule. This is similar to NACL rules, they're numbered. And in the bibliography there's a video showing the AWS WAF console in every year of its existence. Earlier we said that the action can be allow, deny, or count. We asked what the point of count was. To understand why they're useful, we need to think about what you're doing with a firewall. Most strategies depend on things you already know. If you want to implement a deny list, you need to know who the threats are in order to explicitly mention them in a deny rule. It's very reactive, because you're being threatened by something and then you're reacting by coming to know it and then installing a rule. Direction of fit. What count allows is a firewall that allows you to gain new knowledge. Previously, the administrator has knowledge about which IPs are threats, for example, and shapes the firewall accordingly. The revolution that occurs with count is that now the firewall is shaping the mind of the administrator, because it is informing the administrator of how many requests a particular IP has made. The firewall can then be configured. Nate Dye explains that a helpful distinction is that between a static and a reactive policy. He said, so I think most people would think of WAF rules as like firewall rules. They would like to have a set of rules that they know are good. They won't generate any false positives by blocking legitimate requests. But I think in customer conversations that static policies are really tricky to get right. The more rules you add, the more potential there is for false positives. A really common theme is that most customers are relying more on reactive policies. The idea is that the count mode detects candidates for a deny list. The slide below shows how CloudWatch metrics can measure when a source has exceeded a threshold. So CloudWatch, which is the Amazon monitoring service for AWS, where you have entities called CloudWatch metrics, which are just specific things that you measure. So you might measure the CPU on a virtual server, how hard is the CPU, the central processing unit, working. You might how hard is the memory working, but you can measure all sorts of things. We might measure how many requests are being blocked. So count mode will have an alert on CloudWatch metrics. We'll get sampled requests and we'll add the bad IPs to a blacklist. That's a slide from 2015. We're given a suggested rule order. 1. Whitelisted IPs allow. 2. Blacklisted IPs block. 3. Blacklisted signatures block. 4. SQL injection counts for that. And suspicious activity count. So 2 examples of count in that list of 5. And the default action will be allow. Network firewall. In 2020, AWS, they demonstrated that they were starting to think of interesting ways of pushing boundaries. Hospitals, which require medical records to pass between departments, they are limited by incompatibility problems. But in 2020, Amazon HealthLake was announced. It's machine learning specialized in disease and medicine categorization. In 2020, AWS Proton was announced, allowing large corporations to provide a platform for internal development teams. Their developers, their internal teams who develop applications. There's often a boundary between the developers, focused on speedy deployments, and the infrastructure team, focused on standardization. Now, platform as a service might help here, but this involves maintaining your own software. Enter Proton, which sits at this boundary, binding the developer team and the infrastructure team like an actual Proton. The power of Proton is really in that schema file, because this is how you're saying, in the words of Alvarez, one of the product designers on AWS Proton, the schema file, you're saying, all right, I've abstracted all the complexity away from you. Here's the 5 inputs I want you to worry about. We're talking to the developers. Here's the 5 inputs I want you to worry about. Go ahead and create your environment or service. It contains a list of all those parameters with their potential input values. In 2020, AWS also released AWS Panorama. This is for organizations that have cameras on their premises and have computers which use the cameras to perceive things. For example, an airport can have a camera fixed on a lane of cars. If a vehicle stalls, this can be perceived and a staff member alerted. As soon as a camera can see a human in a shop, we can collect data about where they stand. We can observe which aisles generate certain walking speeds, and so on. So as well as HealthLake and Proton and Panorama, 2020 was the year of the AWS Network Firewall. Recall that SGs are on the ENIs, NACLs are on the subnets. And while SGs protect servers generally, WACLs are specializing in protecting web servers, or things at layer 7. And the AWS Network Firewall operates at the VPC level, right? And the VPC is your network. Recall that your VPC seeder is divided into the subnetworks within it. So the network firewall is at a layer above the NACL. This is a rich firewall with many features, so let me try and bring some order to some of them. In practice, we need to modify route tables, right? In practice, if you're going to work with network firewall, you've got to get dirty with route tables. The user guide says, to enable the firewall's protection, you modify your Amazon VPC route tables to send your network traffic through network firewall endpoints. We'll return to that later. At the moment, AWS think of their network firewall as 3 components. Firewall, the firewall policy, and then RGs or rule groups. It can actually be somewhat tricky to articulate how these 3 things are teased apart. After all, usually we say that a firewall policy literally is just a fancy name for a group of rules. That is, a rule group. So these 2 things seem to be the same, a policy and a rule group. And surely even a firewall is nothing but a set of rules. Isn't that what a firewall is? So how do these 3 elements differ? Well, each allows a different degree of modularization and reuse. We can be most reductive about one of the concepts. rule groups. Rule groups truly are nothing but lists of rules. The idea is that a particular RG can be slotted into a firewall policy in the way multiple layers of ink are compacted into a printer cartridge. Multiple RGs can be slotted into a single firewall policy. In one sense, RGs are like templates for how to configure your firewall. Templates can be used again and again. Sometimes they can be managed for you and imported and so on. You might lean over to the fence to your neighbour and say, surely have you tried using this new latest RG in your policies? It's all the rage. AWS tell us that a rule group is a reusable set of criteria for inspecting and handling network traffic. A set of criteria for inspecting that traffic. You add one or more rule groups to a firewall policy as part of the policy configuration. The problem is that if I was sat chatting on the bus and I told you I've come up with an idea, namely a set of criteria for inspecting network traffic, you would laugh because we already have this. It's a firewall. So what exactly is the component in network firewall called the firewall? Well, we can think of this as a unique instantiation of a firewall policy bound to a particular VPC. A firewall must be loaded with exactly one firewall policy. The firewall policy is the printer cartridge, and suppose that printers commit to one cartridge. Rule groups are nothing but rules, it's true. They stay silent on the question of what to do when no rules are matched. They don't have anything to say about that. To work out what to do when no rules are matched, we configure the firewall policy. The firewall policy allows you to specify different default settings for full packets and UDP packet fragments. Network firewall silently drops packet fragments for other protocols other than UDP. The action options are the same as for the stateless rules that you use in the firewall policy's stateless rule groups. You are required to specify one of the following options: pass, discontinue all inspection of the packet, and permit it to go to its intended destination. Pass, move on, go through. It's a good thing for the packet. Drop, discontinue all inspection, block it from going to its destination. Or forward to stateful rules. Discontinue the stateless inspection and forward it to the stateful rule engine for inspection. So that's pass, drop, forward to the stateful rules. So what you can do with the firewall policy is toggle the implicit action. Will the firewall be implicit allow or implicit deny? Of course, they prefer the terms pass and drop over allow and deny. The third option is, of course, the interesting one, which involves forwarding to stateful rules. So let's not be subtle about this. You can choose both stateful rules, like in a security group, or stateless rules, like in NACLs. Recall that the SG sat within the NACL, but our firewall can have stateful rules sat alongside stateless rules. This is new and interesting with this AWS network firewall. With SGs and NACLs, there was an idea of stateless on the outside. This idea remains. Notice how the option within AWS Network Firewall is forward to stateful rules. It's not forward to stateless rules. The interrogation by the stateful rules only occurs after we've checked all the stateless rules. Why? One firewall policy, that's a question for later, one firewall policy can be reused in lots of different firewalls. And obviously that's the same that RGs, rule groups, can be reused in different firewall policies. However, as we've noted, while a firewall's behavior is dictated by a single firewall policy, a policy can be an aggregation of multiple RGs. Any particular firewall is given properties such as 1. A unique name you assign, some tags and a description. 2. The firewall policy which is slotted in, exactly 1. 3. The VPC which the firewall is to protect, exactly 1. 4. Whether deletion protection is enabled for the firewall. So those are some of the mundane attributes. Of course, some of them are very important. They show that the firewall is not a reusable item. More interesting are the following attributes. We've got 5 subnets. What subnets are we going to use for our firewall endpoints? Remember, we have to direct traffic to go through the firewall endpoint. You can specify up to 1 subnet for each availability zone that your VPC is in. Logging. The type and location of the logs that Network Firewall provides for the firewall's stateful rules engine. Remember, it's stateless onto the stateful rule engine. You can enable flow logging for the network traffic that passes through the stateful rules engine. You can also enable alert logging for traffic that matches the stateful rules that have an action setting of alert or drop. So you specify your subnets for your firewall. That's the 5th thing, the 5th property, the subnets of the firewall. Let's now return to this statement about how things work in practice then. So we said to enable that network firewall, you modify your route tables. Any given route table is associated with one subnet, and you modify them to send your network traffic through the network firewall endpoints. So it's like report to the firewall. As our story of AWS firewalls reaches an AWS network firewall, we need to recalibrate our conception of a firewall. The smart security group is like a tight plastic wrapping which ensures the ENI remains sterile, but capable of being pierced with allow rules. Then moving further out, the dumb knackle consists of rules controlling what passes through the boundary of the subnetwork. A WACL can protect a web server, usually by protecting a CloudFront distribution, actually. Well, so far, the firewall has been an integral part of that which it protects, like a layer around the outside. The AWS network firewall does not guard a subnetwork, but rather the whole network, the VPC. However, we need to depart from that conception of the firewall as integral to the thing it protects. There's in fact more flexibility. Rather than every VPC being wrapped in a firewall around the outside, you place something called a firewall endpoint within a subnet of a VPC. The firewall endpoint must be encased in a subnet, and it is recommended that you don't use this subnet for anything else. We'll call it the firewall subnet. Shaquille and Vaganov write, as a best practice, we do not use AWS Network Firewall subnet to deploy any other services, since AWS Network Firewall is not able to inspect traffic from sources or destinations within the firewall subnet. There's something counterintuitive here. If I wanted to place a protective boundary around the outside of my VPC, how is it going to help for me to hide away something within the VPC? The answer is that within AWS, there's a mechanism for ordering all traffic where to go, and the orders are found in route tables. Using route tables, we can order, as in command, any packets entering our VPC to immediately report to the firewall subnet for inspection, and the same is true of traffic leaving the VPC. Route tables. Route tables have 2 columns. The column on the left is entitled Destination. The rows here will have a CEDA range written in. The destination covers the limit of the packet's travels. Where will it stop? I say covers because whatever is written in the destination column of a route table is not necessarily the specific destination of the packet. Rather, it covers the destination. It does at least have to cover the destination. I'm saying it doesn't need to be completely precise, but it does need to cover it. There's a column on the right entitled Target, and this gives the traffic something tangible. Target is tangible. It gives the traffic something to aim for. It's the means to the end. AWS call the target the gateway, network interface, or connection through which to send the traffic. The target makes the traffic move. It has the same motivational kick as a shopping list, or the desired capacity parameter in EC2 autoscaling, or an administrator's recovery point objective. The route table is a list of rules. Sometimes the destination column will simply have all zeros, like this. This destination covers everything, and it's similar to the indestructible rule which lurks at the bottom of NACLs marked by an asterisk. When you create a default VPC, AWS pre-configure the route table with an entry with all zeros, with the tangible target set to be the internet gateway. And this rule covers all traffic, and it points to the internet gateway. And an internet gateway is a component that can be wedged into the wall of a VPC. The VPC created has a /16 seeder block. This means that the first 16-bit positions will be used for identifying the network, leaving 16-bit positions for identifying hosts. There are 32-bit positions overall, so if the first 16 are for identifying the network, the last 16 are for identifying the host. I call it the structural slash. It doesn't tell you anything about the content of the network ID or the content of any IP address. It's a structural slash. Now, since each of these 16 positions, let's talk about the network ID, I think. Each of the one position is limited to two possibilities, either 1 or 0. Well, then we can work out the maximum number of hosts. It's 2 to the power of 16. Okay, so we're talking about the 16-bit positions that we use for the host. Each one is either going to be 1 or 0, but we could be talking about anything for this example to work. We could say that it's a parking space and it's either a red car and a yellow car, or we could be saying it's a counter, and like the counters used in some board games, and it's either a red counter or a yellow counter or a black counter or a white counter. The point is there are two possibilities. So if there are 16 positions and 16 parking spaces for the cars, to find out how many possibilities there are, we do 2 to the power of 16. 2 multiplied by 2 multiplied by 2 until we've written out 16 twos. The answer is we can have 65,536 hosts. So when AWS stipulate that your VPC will, of the 32-bit positions, use only the last 16 for hosts, it is stipulating a limit of 65,530 hosts in your VPC. Target as local. Often you'll see the word local printed in the target column. The destination will be one of the VPC's seeder blocks. Something like 100.64.0.0/16 or something that's a rough example. This entry, so the local entry, accounts for any desire to let traffic flow within a VPC, any desire. But there is a limit on those desires. They're limited to desires for movement within the VPC. There have been some important advancements in the past few years. You could never route traffic to a specific subnet within your VPC. The local route, with the seeder block for your VPC as the destination, was as granular as you could make your internal routes. Nothing could ever be more specific than the VPC seeder. If the VPC seeder had a /24 prefix, meaning the first bit positions that we use for the network, the pre-positions, that's why it's called prefix, there were 24 for the network. So if the VPC seeder had a /24 prefix, then there could not be a route that was /24. Recall that /24 is more specific than /16. Then, in December of 2019, AWS announced that you could have routes which were more specific than your local route. You could direct traffic to a specific subnet in your VPC. This ability to focus traffic to a particular EC2 instance seems to have been limited on traffic that flowed into your VPC through an internet gateway or virtual private gateway. Deployments with traffic coming into the VPC from outside the cloud, so from the internet or from on-premises, they're sometimes called north-south deployments. So when Sebastian Stormack announced this in 2019, December of 2019, we were showed images like the one below. So you can see we have the internet represented by this cloud icon here. We have traffic flowing into the AWS cloud, hitting this internet gateway, wedged into the wall of the VPC. We've got a public subnet, another public subnet. This is called north-south traffic. Previously, in a route table which had a /16 local route, it would have been outrageous for another route to have /24, which is more specific, but not anymore. Look here. The VPC is /16, and yet here you can see a route which is 10.0.10 /24. It's bigger than 16. It's more specific because we're counting from left to right. We'll have counted 16 parking spaces, 16-bit positions, and then we go to the 17th, the 18th, the 19th, all the way up to the 24th bit position. So because we're going beyond and moving further to the right, it's more specific /24. Notice the route whose tangible target, is the Elastic Network Interface, which is ENI0. Its prefix is /24, which is more specific than 16. The local route has been overridden, something which was previously prohibited. There's a principle known as LPM. I call it LPM, longest prefix matching, which means that to resolve concurrence coverage, cases when two rules compete, to resolve that, the route table opts for the most specific route. Thus, everything will be sent to the appliance. Everything will be sent to this /24. The specific nature of the /24 destination gives it priority. That's called LPM, longest prefix matching. So in that month, December of 2019, this outrageous overstepping of the mark, being more specific than the local route, was an ability reserved for the route table associated with gateways. Two years later, in 2021, AWS announced that route tables associated with subnets could also contain routes which were more specific than the local route. Effectively, they allowed you to set up routes from one subnet in your VPC to another. The 2021 announcement stated, "Today, customers deploy a virtual appliance between two instances by modifying the default gateway of the instances to point to the appliance. With this enhancement, you no longer have to modify the instance's default gateway. You can launch these instances in separate subnets and configure routes in subnet route tables that forward traffic destined for the other subnet through an appliance or chain of appliances." What do they mean by default gateway? Well, they're referring to the internet gateway or virtual private gateway. You'd have a 0000/0 destination, which acts as a catch-all route, defaulting traffic to the gateway. Thus, they call these things your default gateway. Your default gateway acts like a router. This page of notes supports these comments. Typically, in a TCP/IP network, nodes such as servers, workstations, and network devices each have a defined default route setting, pointing to the default gateway, defining where to send packets for IP addresses for which they can determine specific route. the gateway is by definition a router. Okay, so those two words here coinciding. The gateway is a router. The point is that in 2021, subnet route tables could contain routes which were more specific than the local route. Such intra-cloud, intra, I-N-T-R-A, meaning within, not inter, such intra-cloud architectures are known as east-west architectures. Architectures like the following became possible. So we can see we have private subnet A, private subnet B. A is 10.0.0.0/24, B is 10.0.1.0/24. We have a firewall subnet as well, so 3 subnets overall, all in a single availability zone. The route table of the firewall subnet, we have one destination, which is 10.0.0.0/16, which is private subnet A, and it says target local. Remember, subnets are the things that compose a VPC, so even though it doesn't say VPC anywhere, these are the building blocks of a VPC. You are looking at a VPC. So the firewall subnet has a tangible target, but in this case it's the local route. We also have a local route in these route tables. We've just written one route table. It's the same for subnet A and subnet B. So we have that local route 10.0.0.0/16, but we also have 10.0.0.0/24 and 10.0.1.0/24. So the CEDAR range of private subnet A and private subnet B, and the target says VPCE-ID, VPCE standing for VPC endpoint. So what we can do is put in that target, that tangible target column, not the word local, but the ID for a VPC endpoint. The subnet route tables have 24/24 routes. These are more specific than the VPC CIDR, which is /16. We are routing traffic through a middle box. Here there is a firewall subnet encasing an endpoint. This is for AWS Network Firewall.